Okay, we're going to start looking at matrices now, matrix algebra. In this video we're going to look at subsections 3.1 and 3.2 of the A-Level Further Maths syllabus. I have done matrices before on the channel, but this is going to be more specific to the syllabus. There's actually going to be a few more things we haven't covered, and yeah, we'll do some examples that are a bit more geared towards passing the A-Level rather than just understanding matrices in general. There will be a lot of crossover. So the first thing is, what is a matrix? Well, a matrix is essentially just an array of numbers or objects. You can put other things inside, but yes, we'll say for now we're going to deal with arrays of numbers organized in a certain way. The first thing we need to look at before we can consider some operations on matrices is what they look like and some ways we can have of describing them. So we define the size as m, and we use this product notation, m cross n, say, but we're not. What we would say is m by n. That's how we would read this. So we have an m by n matrix where m is equal to the number of rows, and the rows are going across, and n is equal to the number of columns, so the number we have going down. If you're not familiar, this hashtag can be used. There's no the number of, not the number of, but the number, which is helpful instead of writing it all out. Anyway, so we're going to look at two matrices and just quickly define the size. So if we have a matrix containing 1, 6, 2, minus 3, 0, minus 4, 2, 7, and that's an important thing. When you read out matrices, you start on the top row and you read left to right and you work your way down. You don't read this as 1, 0, 6, minus 4. You read it as 1, 6, 2, minus 3, 0, minus 4. Okay? And this matrix is 2 by 4, as you can see. 1, 2 rows, 1, 2, 3, 4 columns. Maybe I should write that in red. Alright. Now we're going to look at another matrix. This one is going to have 1, minus 4, minus 7, 6, 3, 1, minus 1, 2, 4, and minus 11. And this matrix is 5 by 2. As you can see, we've got 2 columns, and 1, 2, 3, 4, 5 rows. Okay, so that's pretty simple. But now we are going to look at some operations. So let's just work in this column here and over here. If we have a matrix A, and the notation I want to use, I'm going to underline letters twice. You might be familiar. So for me, if I write a letter just by itself, it's a scalar usually. A letter with one line underneath would denote a vector, and 2 lines underneath would be a matrix. That's just what I've grown up using, so that's what I'm going to use. And we're going to say that A has size m1 by n1, and our matrix B has size m2 by n2. So if m1 is equal to m2 and n1 is equal to n2, we can define plus or minus b. And the way we do this is, because our matrices are the same size, we'll do an example here. Say we have 4, 1, 3, 2, 1 in matrix, and we want to add, add or subtract. Let's not put the minuses in, just going to make the notation look a bit weird. We'll just stick with positive numbers. We'll go 7, 1, 2, and 5. Square bracket. Well, that's just equal to 1 matrix at the same size, 4 plus or minus 7, 1 plus or minus 1, 3 plus or minus 2, 2 plus or minus 5. So you can see we just add up in what we call an element-wise way. So each corresponding element we just add up, and you can see why now the matrices have to be of equal size, because if one has more rows or more columns than the other one, it's hard to choose, well, it's impossible to choose which element should be added to which other elements in a way that everyone would pick, so we can't define that operation. Second, so I'll just put a little line into that. If n1 is equal to n2, we can define A multiplied by B, where this product sign denotes matrix multiplication. Note that we can define A cross B, but we cannot necessarily define B multiplied by A, okay, so with B on the left, because matrix multiplication is different to scalar multiplication in that way, it doesn't commute. So that's something important to remember. And A multiplied by B returns M1 times N2 by N2 matrix. And this might seem a little bit unusual, but we are going to now show you the method for multiplying such matrices, and see why that's true. So if we take a matrix A to just be, we'll go with 2 by 2, we'll go with 0, 7, 3, and minus 1. And then we're going to define B to be a 2 by 1 matrix, which is a vector, but still can consider it as a matrix. And this is going to be 8 and 12. I'll keep doing this. Square brackets we tend to use. So A times B, or just AB, is equal to 0, 7, 3, minus 1, 8, 12, and we do not define this element-wise. First we have to look at the sizes of these, so these are 2 by 2, this is 2 by 1, so these match, so that's good, that's what we want. Actually I want to do this in red, but remember the size of the matrix that we return is given by these two, so that is in fact 2 by 1 matrix. I still might want to make this a little bit bigger, just for the method. I'll put the second bracket in later. So what we do is, for our matrix on the left, we work across the rows, and for our matrix on the right, we work down the column, and we perform dot products. Okay, so for the element, and this is the element here, is in row 1 and column 1 of our new matrix. So we perform the dot product between row 1 of the first matrix and column 1 of the second matrix, which is 0 times 8 plus 7 times 12. So if you're not familiar with the dot product, be sure to go and revise upon your vectors. But essentially, if we've got two vectors, one with A1, A2, and this is defined for vectors in R3, R4, whatever. But in this case, we're dealing with R. You just multiply the corresponding element and then add up the products. Okay, so you can see that's what we've done here, and then we're going to get, for this one, so this is the second row, still first column, so we're going to go across the second row of the first matrix and down the first column of the second matrix. I think I said this was the second matrix. Okay, anyway, so that's 3 times 8 minus 1 times 12. So this is equal to 0. My arithmetic. If I made any mistakes, just let me know in the comments. And that's 24 minus 12, so this is equal to 84 over 12, and we can actually bring out a factor of 12. This gives us 12, 7, 1, and you can do that because the way we multiply a scalar by a matrix is we just multiply each element in the matrix by the scalar on the outside. Okay. That's all we're going to look at for addition operations on matrices. Next two things we're going to do is look at some special types of matrices. So first of all, this notation denotes the zero matrix, and this is equal to a matrix of zeros. And obviously you'll need to know sort of what size matrix you're working with. You might want a 3 by 3 matrix, 3 by 3 matrix, or 2 by 2. Yeah, because this doesn't give us any indication of the size, but it's just a matrix where every single element is 0. So, for example, that's a 0 matrix. And then we're going to define an identity matrix, and we'll see in future videos the properties this has. But first we need to define a square matrix. Square matrix, if m is equal to n. So basically, if the number of rows, is equal to the number of columns. Okay. So now, an identity matrix is a square matrix with ones in the leading diagonal and zeros elsewhere, and we're going to look at an example or some. So I2 would be a 2 by 2 square matrix. I3 would be that matrix, and so on. Hopefully you can see what I mean by the leading diagonal. It's just we start in the top left corner and go down to the bottom right. Okay, so obviously there's a couple of diagonals we can define here, but that's what we call the leading diagonal. Okay, that's what we're going to look at for this video on matrices. The next video, we're going to motivate on why we even need matrices, what they can do, and some geometric interpretations of matrices in particular relating to graph transformations. If you do want to get ahead, then be sure to check out the previous videos I've done on matrices, which I will leave a link to the playlist somewhere around this video. I hope you did enjoy it. Please like and subscribe, and I hope to see you in the next one.